Hey guys, I'm Jose and this is tutorial number 22. We're going to start seeing physics. So we're going to start with springs. Okay. So let's start a simple setup in 3D. Right. And we're going to do a very simple setup as we usually do with a PCCam and OpenGL in this case. So some people have been asking about OpenGL, so we're going to use OpenGL. Background 0, right. So for OpenGL to work, the first thing that we actually need to do is import the OpenGL right. And we're going to import another few things, right? So we want to work with PCCam, so we want to import. Let's do it like the other way, that is perhaps faster. Import PCCam. We want to import from Verlet Physics, right? So all this stuff here we don't really need. We'll see exactly what we need. We're gonna say this one we don't need, this one we don't need, and this one we don't need. Right? That's the problem when you import things like this. You actually get out of stuff that you don't really need in this case. Actually, these two also we don't need. So we are sticking with that. The other thing I'm gonna do is import just Toxi to actually work with vectors. Geom, right? And I think that we are good to go for now. Let's see, we're not having any problems. Okay, right. So let's do an instance first of all of the camera, right? In order to see our 3D space. So cam equals new is command. And here what we're gonna do is just as usual a box, right? So no fill and stroke white. So fairly simple, what we have been doing almost every 3D tutorial. So now we're going to start bringing in some of the physics components and to start seeing how we can actually start working with those. Okay, the physics library from Toxiclips works in the following way. You need to first import, make an instance of a class called Verlet Physics. That will be the solver, physics, right? So this is the physics engine, and we're going to start putting stuff inside, right? Like behaviors of gravity, like particles, springs, everything inside this kind of little world called physics. And then we're going to just say update or run to this world, right? And everything that is inside there would get computed and get calculated with each other. So that's the key. We're gonna call it the solver, right, or our world. And now we're gonna start bringing in some stuff that we're gonna start using, right? So Verlet particle, right? And I'm going to call it particles because this is going to be the container for all the particles that I will work with, right? Let's check that we don't have any syntax mistakes, and we are fine. So now we need to initialize this physics space, right? So we're going to say physics equals new Verlet physics, right? Quite simple. We just have our space, our solver initializing in the world. And now we're going to start introducing, like, putting particles inside that space. And we want to say here in the draw, just somehow to draw every particle that is inside that system, right? So let's add a bunch of particles there, and then let's see if this actually works. So how do we add a particle? We're gonna say Verlet particle. P equals new a Verlet particle works exactly like a vector, right? It's actually a vector with a few more things to it. Using the idea of inheritance. We'll see what its inheritance in some further video, but for now just consider that a particle is very similar to a vector. It's actually the same. So we're gonna say something like this: Verlet particle in the 0, 0, 0, right? I probably spell it wrong, so we're gonna say, yeah, that's better, right? Yet we don't have anything in the world. What you want to do when you do a particle like this one, the next thing that you want to do is say p dot or physics, sorry, dot add particle p, right? So what this little line here is saying, it's saying pick this particle that you created and add it to the world, right? Add it to my solver. So now that it's inside the solver, it can get calculated. If it's not in there, it won't get calculated. Still, we don't see it because we're not basically drawing anything on the screen. So we're gonna do a little for loop here. We're gonna say basically go through every particle in the system and draw them. For integer I equals 0, I smaller than physics dot particles. This is a the particles is an array list that it's inside the world, the solver physics. So this is something that I know. If not, if you don't know this kind of what fields are inside the physics class or the Verlet physics class, just refer to the toxic clip reference. So this one I know because I have checked it before. That is the list of particles, and we're gonna say I++, right? And so for every particle, we're gonna cast it. Say Verlet particle. This name could be anything. VP, right? When you're doing this operation here, people usually kind of get confused with other calls. Like what we're doing within this parenthesis is it's only visible within this parenthesis, right? So the names that you're giving to your particles could be the same all the time, right? They don't refer to the same thing, but could be the same. Right, so we're gonna say Verlet particle VP. Is from the class Verlet particle. Go to this array list and get the element I, right? And then we're gonna say stroke weight 5, stroke 255,0,0, right? And point in vp.x, vp.y, vp.z, right? Each particle has a component x and y and z, basically in position, and we're doing a point wherever that particle is, right? So let's see if we're having any mistake. We're not, so that's great. The only thing is that we're getting that stroke thickness also to the box. So we have one particle in the middle of the screen, right? And that's perfect. We created one particle. But what if we want to do many particles, right? Like, as we have done it before, we can do this in a for loop, right? So we're going to say for integer I equals 0, I smaller than 20, I plus plus. And what we're going to do here, it's going to say, let's say that in x, we're going to use I, so each time times 5, something like that. Let's see what we get there. So now we have a sequence of particles, right? And these particles are just there in the space. We don't have any kind of physics working. Even, I mean, we're not even calling the physics engine yet. It's just showing the particles that are inside that container, right? I want to just do this a little bit bigger for the purpose of being able to see it better. What we want to do now is just let's call that physics engine and let's see if it does anything, right? So what is the main function that we need to call, and we're going to do it here at the end. We're going to say physics.update. Right, so this is gonna call basically it's gonna calculate any physics behavior in our world. If we see what is happening, it's nothing happening, right? So we don't have anything going on. We have particles in the world, but we don't have gravity or anything that really could get computed. So we actually need to bring in some behavior. So let's bring in one behavior. We're going to put it here. It doesn't matter really where we put it, but it needs to be in the setup. So we're going to just add that behavior once. And as I'm using ToxicLib's version 20, this is the version for the version 20. If this syntax that I'm going to write right now doesn't work, is because you're probably working with an older version. Some of these behaviors change in the last version of ToxicLib. So please update your Toxi library and then you should be ready to go. So let's say gravity behavior. Right, so we're going to call it G as gravity equals new gravity behavior. Gravity behavior needs a vector to work. A vector that we don't really have yet. So we need to produce it, right? So vec3d b equals new vec3d, and it would be 0, 0, minus 0.1, something like that. And then we're going to say, so right, we have a vector, and this vector is suggesting which is the gravity direction for this gravity behavior. Now we have to link this gravity behavior with, basically add this behavior to our physics solver. If this is not linked by to this solver automatically, so we need to do that. So we're going to say physics dot add behavior G. So you can notice that what we're doing here with the particle is exactly the same what we're doing with the behavior. So we're adding different elements with different kind of qualities, and the solver can actually make those interact. So that's a great thing about the class, the early physics class. So let's see if this is actually working. Yeah, you can see that now we have some gravity going on there, right? The little particles just disappear in the bottom of the screen. So that's great. Particles are working. So we can decrease a little bit the gravity to see them a little bit better. That's done by decreasing the vector, but you can see that they are getting acceleration, right? So that's really kind of how physics work. The vector is an initial gravity, but if you keep adding this gravity on and on, the particles keep getting accelerated. So that's really neat. So what do we want to do now? We don't want these particles to really fall all the way through, right? We want to just say, let's see how we can actually lock them. We're going to say if I equals 0, right? I'm writing this here in the for loop, and we're going just to say that, just to suggest that one of these particles, the first one that we create, we will say, so we're saying if I equals 0, p dot lock. We're locking the particle, right? So let's see if this is actually making any difference. Right, so this is what we're doing right now. All the other particles are being dragged down by the gravity, and we have the first particle that it's locked, that it's not being dragged down. So that's what lock does. Every particle can get this quality of locked, and we can unlock them as well. So that will make them hold position. So let's do something that, for me, it's really interesting, and we often use it in workshops and in our work. We want to use color as information, right? So right now we're using, let's say, we're saying draw particles, right, and draw them red. But I will say, why don't you draw them in some green color, let's say something like that. And we're going to do a little if statement. The following. So let's check the color that we have right now. So this color, it's some sort of bluish, greenish color. And we're going to say if VP, the particle that we're evaluating right here, dot is locked, right? It's locked. It's a little function that will tell me if that particle is locked or it's not locked, right? So it's a boolean. So we're gonna say if it's locked, painted red, right? So we're gonna say stroke is 255,0,0, right? That's red. Else, the particle will be painted green. And this is a very simple if statement that changes the color in which particles appear in the screen. Let's look at it again. If the particle is locked, the stroke is red. If it's else, so if it's not, the particle is green. Let's see if this is working. Right, so we can see visually which of our particles are locked. And that's the way that you start kind of seeing the data that you're actually building up, and especially when you start producing behaviors that are quite complex, you want to see exactly what is actually going on. So I really recommend do these kind of techniques to actually show some of the information. So okay, we have one locked particle, and now we have we're drawing them and everything, and that's great. What are we missing to just finish this? Actually, we wanna do springs, right? This is the video of springs, so we should do those springs. So we're gonna do another for loop. We could do it in the same one, right? But I'm gonna do it separately because just to make everything kind of nice and independent, so we don't get the stuff too complicated, right? So we're going to do another for loop that will be exactly the same like as the first one. So it's going to say from integer I equals 0. So I'm going to just copy this one. Right. This one we're gonna do it a little bit different. It's interesting what we're doing here. We're looping through as many particles there are in the system, right? So we're gonna do that, and we're gonna say loop through the particles, right? And get me the particle I. This is what this line is doing. VP. And what we're gonna do is just also give me the particle that is behind that, right? So let's call VP1 and VP2. The problem with this method is that if we run this now, we're gonna get an error, because especially when we ask for the element 0, and this element 0, I will be 0, and we ask for the element -1, the element -1 doesn't exist. So we're going to put a 1 here, just to be able to ask for 2 particles each time. The first one will be 1, and the -1 would be 0, and all the rest of the particles we can actually ask them. Why is this? Why do we need 2 particles? Because springs work with 2 particles. You need to. The spring is a link. It's an elastic link between 2 particles, right? So we're gonna do one now, and we're gonna see how that works. So vert spring SP equals a new vert spring, and here this is a constructor of the verted spring. We need to provide the particle 1, that is VP1, comma VP2, that's the second particle, and we have 2 values. The first value is the length, or the rest length of the particle, of the spring. So this spring, if it's at 10 units, it would be okay. That's kind of the length of that force. And then we have 0.1. This is going to be the dampening. So this is how strong this spring is. So let's see if this is working. That's cool. We don't have this spring as part of the system yet. We have to do exactly what we have been doing before, adding this spring to the system, right? So we need to say physics.add spring SP, right? And this will actually work, but we won't be able to see the spring. So we could do a little loop just like this one, where we say go through all the physics, collect all those springs, right? So let's do that loop just to finalize this little sketch. We're gonna do another for loop, right? Completely independent of the first one. We're gonna say instead of particles, we're gonna go through the springs inside. I know that, again, physics is the world, and it contains a little collection of springs that we're gonna use, right? So Berlet spring SP equals from the class Berlet spring dot get I, right? So we're getting the element I. Every element, we're going through every element inside that list, and we're gonna say stroke 2 by 5, so white, and stroke weight 1, and we're gonna say line Between what? Between sp.a.x. What is this? This long right? And spline has both A and B. There are the two nodes on each side, and each node has an X, Y, and Z, right? So what we need to do is say this is going to be the first node of the line, the XYZ of the node A, and this is going to be the XYZ of the node B, right? As I said, the spring is the connection between the 2 points. One of those points is called A and B. This is the way the class was written. So it has a feel that it's like basically two vectors, right? Vector A and vector B. And we're using those coordinates separately to draw a little white line. So we should have it working right now. Let's see if this is working. So there is a line. And you can see now that basically the spring, it's linking these particles together, right? We are drawing each one of the springs separately. We are drawing each one of the particles separately. We have a gravity behavior working independent with a vector, right? And we're creating, in this case, 20 particles. This is what actually defines the population of particles we're working with, because this for loop here, the one of the springs really, it just goes, it connects all the springs, basically. That's what the only thing that it does. And we can see that we have a very nice rope kind of connection. We could do more particles if we want, say 40. And this should work exactly the same, right? So the way the script was written is allows for variation of the number of particles. You can play with different things. You can go and check into Toxiclipse how to change the mass of the particles, or lock some other ones and see what are the results. You can do catenary models and all that kind of stuff that everybody's so crazy about lately. So yeah, that's it. I hope you liked it.